Good morning or good afternoon, whenever you're watching this. I'm going to continue on with our tail pitching moment calculation. Where we left, we had this formula. So this is the moment arm times the lift, so it's force times moment arm, and then we called this VH, horizontal tail volume ratio. Now LT is measured from the CG, if you remember, back to the aerodynamic center of the tail. Which is fine, except sometimes, in fact, often the CG can be in different positions. So that means LT changes whenever the CG moves to a different position. Sometimes it's convenient to use another dimension called LT bar. That's measured to the aerodynamic center of the wing. If you remember the dimensions that we gave for that, aerodynamic center is located aft of the datum or the leading edge, and then the CG is measured with the letter H. And so the difference, sorry, that has to go all the way back here. Scratch that. The CG is back here. And so the difference between those two dimensions is the difference between LT and LT bar. So that distance right there. So we can write LT bar is LT plus that difference, that extra distance, and then substitute that for LT up here and get an expression for the pitching moment of the tail in terms of this LT bar, this new distance. Let me leave this so you can see it. So then we end up with CMT is where we solved for this, sorry, to substitute up there. So that gives us a new expression, and typically we will write this combination, get a bar here, we'll write this combination, and we'll call this VH bar. So up here, VH was that ratio in terms of LT, and down here, VH bar is that same ratio in terms of LT bar. So you get CMT, VH bar, CLT, plus this extra part that we get because we changed the distance that we were measuring to the tail definition. So sometimes this is nice to use, this version, and in fact in the text and in class we will use the version in terms of VH bar sometimes, and we use the version in terms of VH sometimes. So that's two expressions, this one and the one above, for the pitching moment of the tail. And we'll need to add that to the pitching moment of the wing. We're not going to do that today. That will give us the total pitching moment. But the other thing that we need to talk about, and this is on the homework, is that the engine can produce the pitching moment. And so we need to draw a free body diagram or a picture of the engine thrust line. So there's the center of gravity. We're going to be taking moments about that. We say that the engine thrust acts down here, defined to be the distance LE aft and ZE down. Obviously the E is for engine. So this is the thrust line, and the angle that it acts here is called gamma E for the engine. So it's not too hard here to take pitching moments. We just take T cosine gamma E times ZE, and that'll be positive, and then T sine gamma E times LE, and that'll be negative, and that gives us the two pitching moment components for the engine. So the pitching moment for the thrust so again, there's the horizontal component times ZE, nose up is positive, so we have a plus sign here. And then here is the vertical component of the thrust times the LE moment arm, and that's negative because that gives a nose down pitching moment. And then we divide this whole thing to get a coefficient. And the C bar non-dimensionalizes these moment arm distances. And the Q bar S non-dimensionalizes the thrust force. And so we'll define a thrust coefficient. Is CT is T over Q bar S. To get this more compact, to give us a formula for the pitching moment in terms of coefficients. And with all these formulas, when we're done, you can look at this and say, okay, the moment is caused by a force times a moment arm. Force times a moment arm. Let's go back to our diagram here. We also want to be able to calculate the component of the thrust in the lift direction and the component of the thrust in the drag direction. So for that, we need to throw in the relative wind, because lift and drag are calculated relative to V infinity. So let's draw a V infinity vector here. And then this is the angle of attack here. And so the thrust in the lift direction is going to be the component perpendicular to V infinity, and the thrust component in the drag direction is going to be parallel to V infinity. And so the angles that we need to use to get those components, let's draw those in red right here. So we're going to have a component here and a drag component that direction, are going to be sine and cosine of gamma E plus alpha, because that's the total angle. So T sine of that is going to be this vertical component. T cosine of that is going to be the horizontal component. So that gives us the lift and drag contributions of the thrust. And that's important because if we tilt the thrust vector up, then we can get some lift from the thrust in addition to the wing. So the lift due to the thrust, or the thrust component in the lift direction, I better say, is that. And then we can turn it into coefficients. So then that's lift coefficient. And this is thrust coefficient. And then we get the drag due to the thrust. Notice the way we defined it is that thrust is forward, so we get a negative component. And then we can do the same thing and we get the drag coefficient. So let's scroll back up and review. We had already derived a formula for the pitching moment of the tail in terms of this dimension. So all we did was shift the distance that we're going to use to the tail, measured from the AC of the wing, because it does not move with loading, shifting cargo and people around. We just substituted. We found this expression, LT in terms of LT bar, and substituted to get a different form of the pitching moment of the tail. And then we looked at the engine, because the engine is going to create a pitching moment as well. We need to take that into account. And we also get lift and drag from the engine. And so it's just components of the thrust line, T, in the appropriate directions, times the appropriate moment arc. All right, the last topic that we need to do today is we need to talk about adding the lift of the wing and the lift of the tail together to get the total lift of the airplane. So the first thing we need to remember is the lift of the wing body acts perpendicular to V infinity, and the lift of the tail acts perpendicular to V prime. Remember, we had V infinity coming in, and then the downwash at the tail reduced that angle by a downwash angle epsilon to V prime. But we've been assuming that a lot of these angles are small, so we're going to say epsilon is small, so that the lift of the wing body and the lift of the tail can just be added together. So that's easy. It's like everything else, we're going to turn this into a coefficient. Divide by Q infinity S. And remember, like we did last time, when we calculate the lift coefficient of the tail by itself, we do it in terms of the tail area, ST. Because we do the airfoil, we build up the tail in terms of its own area. So we have to multiply by its area to get the total lift. So we're going to end up with, once we substitute this in here, this becomes the coefficient. Q infinities cancel out. Then we end up with this tail area ratio that always shows up. It showed up in the pitching moment. Remember when we saw that? It shows up here. All right, so then how do we, let's put an equal sign here. How do we calculate the lift of the wing body? It's the lift curve slope times the angle of attack. So that's our linear lift model. Now, how about the lift of the tail? We need that here. So it has its own lift curve slope that we would calculate using that big formula, multiplied by the angle of attack of the tail. And remember from last lecture, the angle of attack of the tail is reduced by the downwash and how much we tilt the tail downward. We drew a big picture of that last time. We said, well, the tail might be tilted down by an amount, an angle IT. So this is not hard. We simply do some algebra. We add all this stuff together. The last piece of the puzzle is we need what's called a downwash model. This simply says that the downwash at the tail is modeled as a linear dependency on the angle of attack. So as the angle of attack goes up, the lift goes up, and you get more downwash because you get stronger trailing edge vortices coming off the wing. So that goes in here. And then we add the whole deal together. All right, so all I did was substitute this formula for the angle of attack there, what we had before. And then we look at this and we say, okay, this stuff multiplies alpha wing body, and the other stuff does not. So let's collect two different terms together. Let's collect all of the stuff that does not multiply alpha over here. And then factor out alpha wing body, and here's all the stuff that does multiply it. So let me get a different color here. So now we're going to rename some of this stuff. We're going to call this CL0. We're going to call this the lift curve slope of the entire airplane, because this formula is really a line that models how the lift of the entire aircraft changes with alpha. Then we could draw a plot of this, the lift curve for the entire aircraft. It's just like any other lift curve. The intercept is what we've called CL0, and the slope is what we've called A. So this is our lift model for the aircraft, and we'll need that when we want to calculate the total lift of the airplane. As before, when we've done this with the wing by itself, we defined a zero lift line, which really means that we simply redefine a new axis system on this diagram. Instead of measuring the alpha wing body, we're going to define a new thing called alpha of the aircraft. That's the distance from this new axis. So this is the alpha axis. So really it just amounts to shifting the definition of alpha by that distance, which is negative CL0. So the easiest way to do this is to just say, okay, we're going to factor out A in the formula that's still on your screen above. So if we factor out A, this thing here is what we're calling alpha in the picture above, because it's the slope A starting from zero lift, marching up the lift line. So this is, we're defining alpha, the angle of attack of the aircraft, by exactly that formula there. So that gives us two different ways to write the lift. You know, you're going, wow, we got two ways to write the pitching moment, two ways to write the lift. Different formulas are convenient for doing different calculations. We can calculate CL like this, or we can calculate CL in terms of the angle of attack of the airplane as opposed to the wing body, and then we use this formula here. So here are our two models for the lift of the total aircraft. Now, if we want to add the engine in, and in your homework, I've told you not, we'll derive the engine formula, but we don't add it into the lift. But if you were going to add that in, you would simply add the CL of the engine in to that as well.